I'm Aditya Prakash. I'm on Team BionUX, and we've created a transhumeral prosthetic arm with haptic feedback. This arm is a low-cost 3D printed arm that allows users who have lost their arm above the elbow to have an arm now to grasp things. So we have 1 degree of freedom on the hand. And we also have sensors on the fingertips that allow the user to have a sense of touch again. And what they can feel now is pressure, temperature, and acceleration, which is then presented to their residual limb with motors on the upper arm interface. The arm can basically be divided into 3 parts. Sensing the touches, so sensing pressure, temperature, acceleration. The other part is feeling the touch, so pushing these motors into the skin, vibrating the LRAs. And the final one is the integration with the body, so using muscle signals to actually move the hand. So we can start with the electrode. What the electrodes are measuring are EMG, or electromyography, so that's measuring the voltage differential between 2 points on a muscle. And what we're doing is monitoring this over time, and we have an algorithm running on the Intel Edison to detect whether someone is exhibiting a low level of activation, a medium level of activation, or a high level of activation. We have a board, a Grove board, that does a lot of the filtering and amplification, rectification for us. So the real, engineering is in the algorithm side. So what we're doing is using a sliding window algorithm. So what we're doing is collecting these EMG samples at 1,000 hertz, and when we take 128 samples, what we do is we do something called feature extraction. So we're taking the most important components of the signal. This includes the maximum, the mean, the entropy, the variance. So that's all in the time domain, but we also look in the frequency domain. So using a fast Fourier transform, looking at the principal, like the main frequencies within the signal. And what we do is we collect these and have a classification for them. And what we found is we only need to look for one feature, and that was a custom-made feature that we came up with. We ran an FFT and looked at the frequency bins 1 through 20, and we found that there was a large difference between the 3 levels of classification and this feature. So the low level of activation would have the least power when you sum up these bins, and the highest level of activation would have the most power. So just based on that alone, we were able to differentiate between 3 levels of activation with a 90% classification accuracy, which is really good. Since this algorithm collects 128 samples at a time, the sampling rate is 1,000 hertz, there's a delay of at least 256 milliseconds from my muscle activation to the actual hand moving. And we did some research, and we found that in order to make it a seamless motion, it has to be under 300 milliseconds. Once we have this algorithm running on the Intel Edison, this is how the process would look. So if I'm a user, I would flex my arm, and the electrodes would pick up the voltage differential across the bicep. And once that signal is processed on the Intel Edison, we know which classification it's at. So it's a low, medium, or high activation. And what we're doing now is controlling a DC motor. The DC motor has an encoder so that we know the position of the motor at all times. And based on the classification, the Edison, using a state machine, will move the motor to the correct position and actuate the cabling system, which then closes the hand to a specific position. And as you can see, if I flex, I'm able to flex the hand. And if I relax, the hand is relaxed as well. We chose the Intel Edison in the end because of the large role it's going to play in the Internet of Things movement. And we really wanted this hand to be a part of you, a part of your everyday life. It's not just something you charge overnight and then just throw on. We want it to be a part of your body. And with the Intel Edison, it makes things really, really seamless. It's low power. It has the Linux environment, so we can make this thing multi-threaded. It just provided us with a platform that really allowed all this to be possible, the sensing, the actuation, the EMG, and it really beats out any microcontroller because what's a microcontroller going to do? It doesn't have Linux, Raspberry Pi. It's more of a teaching tool. So in the end, if we want this to actually be used by people in the future as a real product, we feel as though we can base it around the Intel Edison and move forward from there.